Some of you might wonder what happens if I keep on compounding interest in smaller and smaller times. So for example, this is once a year. This is twice a year, or semi-monthly, or semi-annually, I should say. Let's rewrite that. Twice a year. So yearly, semi-annually. 4 times a year is quarterly. 12 times a year is, of course, monthly. 52 times a year is weekly. 52 weeks in a year, more or less. 365 is daily, not counting leap years. 5,256,000 is minutely. You might remember that number from that musical Rent. And then 31,536,000, that's seconds per year. And if you compound all the time, continuously, where did we get that number? How do we plug in infinity? If you look at the numbers, they don't change too much. So that infinity is not going to make us $1 million. It'll grow, but not as fast as we would think. Because, yes, we're doing it more often, but we're cutting down the interest to smaller and smaller pieces each time I do the interest. This idea, as n goes to infinity, is something very special that we use in mathematics. And that's what this is. And so we have a very special name for this number, and that number is E. And so this number, and I hope you know this goes on forever. It doesn't stop there. It's just writing down that many digits. So dot, 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 is approximately 2.7. And for the sake of this class, we'll see that E is about 2.7. Like for pi, we see that's about 3.14. Not exact, but close enough for what we want to do. So if you just want to learn a formula, the continuous interest rate is P to the RT, where P sub 0 is the initial or beginning amount of money, E is the number we just talked about, R is the interest rate for the year, annual rate, and T again is the number of years. Okay? For those that care, here's how we came up with that formula. Here's our formula for compound interest. We're going to take this R over N, flip it over, and call that U. So if we reflip it over back to the Rn, then the U becomes 1 over U. We flip both sides over. And if you cross multiply, do you see that we get N equals RU? So R over N becomes 1 over U, and N becomes RU. The T is still there. When I have exponents that are multiplied together, R times U times T, when I have a power to a power, I do the same thing. I multiply exponents. So all I'm doing is rearranging this step to this step. But in continuous interest, where we are compounding all the time, N, or the number of times that we compound, is infinity. Well, if N is infinity, U is also going to be infinity because R is the interest rate. So then the U becomes infinity, and there's our definition of E, where the U goes to infinity. So this portion inside the double brackets is E, and the RT is on the outside, and there's our formula. So in example 2, $8,000 is what we're investing, the initial amount. We have 1.2%. I hope you know that's 0.012. And in the first case, we're going to do this for 6 years, compounded monthly. So 6 years, compounded 12 times each year. This kind of makes sense, right? If we do something monthly for 6 years, we do it 72 times. Crank this out, and we get this answer. If we do it continuously, we use the other formula, P e to the RT, and we get this amount, and we get a little over $4 more. Here, back in the day, something was worth $24. It goes up in value 5% each year, so the rate is 0.05. And if we still go from 1626 to 2020, do the subtraction, that means we're going to go 394 years. Monthly times 12. If it's continuously, we use the PE to the RT formula. And from $24, 394 years ago, we now have 8,140,000 blah 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 dollars, whereas here we do it continuously, it's more, quite a bit more, but again, we're talking about 394 years continuously. And I left off the cents, if that's okay with you. I figure after $8 billion, the cents are not that interesting. What's interesting about the continuous interest compounding is that things like animals and bacteria, they grow continuously all the time. And so the formula becomes more interesting and useful. So here we go. There's the P, the beginning amount. There's the E, there's the R, and there's the T, the time in years. And so we have a beginning population of 1,144, in this case, gray wolves. The growth rate, it's given to us, it's about 3.25%. And X is the number of years. So if we use this model in 2018 from 1978, we have 40 years. The growth rate doesn't change. The initial amount doesn't change. E doesn't change. And if I pop this into our calculator, we get this amount. Just to make sure you know how to use your calculator for this, we have 1,144. E is found over here on the division key. It's blue, so second, and the division key is E. Caret, there's our exponent, 0.0325 times 40. All of that's up there in the exponent position. Press enter, and you would think you would round this to 4198, but we're talking about actual things here like wolves, and so the next wolf isn't quite there yet. And so in this kind of situation, we always round down because the next wolf is not quite ready yet. Now understand, this is just a formula that's supposed to mimic what really happens. And it's pretty good. Because what really happened is there were 4,222 wolves. The predicted amount was 4,197, so they're off by 25 wolves. So this formula is not bad, but the actual number is the actual number. And so we underestimated the actual number. But it's close, so it's a good model. It's a good model.